Hello, everybody, and welcome back to another exciting edition of Ed Puzzle Lecture Notes. Today's daily objectives. Number 1, be able to fill out a monohybrid Punnett square to calculate genotypic and phenotypic ratios. Now, if you have no idea what that means, don't worry about it. By the end of this Ed Puzzle, if you don't know what that means, definitely worry about it, because if you don't know how to do these Punnett squares, good luck in this unit. And number 2, it was the same as one of our objectives in our first lecture in this unit, genetics. Define these key terms. You have to know these key terms or you will not be able to do any of the other problems that are coming up later today and later on this week and next week. The terms are gene. What is an allele? What is a genotype? What is a phenotype? What is a trait? What does it mean when you use the term homozygous? And what do the terms heterozygous and hybrid mean? All right, so I hope you enjoyed this lecture. Hello, and welcome back to another exciting edition of Ed Puzzle Notes. Today we're going to continue in our journey through genetics. We're going to learn how to use Punnett squares to determine probabilities of phenotypes or traits in the offspring. But first we're going to do a little review on these very key terms over here. So a lot of these terms you've probably never seen before. They're totally new. Don't worry, if you practice them, you will definitely learn them. But on the other side, if you don't practice them, you probably won't. Now, first term is a gene. A gene is a segment or section of DNA which codes for a particular trait or feature or characteristic that you have. Now remember, we have 23 pairs of chromosomes. So we have 2 of each chromosome. We get 1 from mom, 1 from dad. So since we have 2 of each chromosome, we also have 2 of each gene. So we get 1 gene from mom, 1 gene from dad. Now, we all have hands and fingers. But how does our DNA tell our body how many fingers we're supposed to have? Well, we all have a gene for this. That particular gene is located on chromosome pair number 7. Now, for those of us that have 5 fingers, like this person over here, 1, 2, 3, 4, 5 fingers, that is a specific allele. So an allele is the different types of genes. Now, the 5-fingered allele is what's called recessive. That means the only way you can have 5 fingers is you have to have 2 recessive alleles. And we show recessive alleles or recessive traits with lowercase letters. We'll use an F for fingers. Now, over here, you can see this person actually has 6 fingers. That is a different allele. This person has the dominant allele, at least 1. And we'll signify that with a capital F. So, lowercase f, or lowercase letters, those are recessive, and you got to have 2 of them. So the only way you can have 5 fingers is you had to give a recessive allele from your mom and a recessive allele from your dad. Now this, when both alleles are the same, either they're both big or they're both little, that's called being homozygous for a trait. The prefix homo means same. So if you have 2 of the same alleles, you're homozygous for that trait. And since they're both so small, lowercase letters, we're going to say you're homozygous recessive. Now, for the people with 6 fingers, I've never met anybody with 6 fingers, but it does happen. They can have 2 different what's called genotypes. You can have 2 different genotypes if you have 6 fingers. You can only have 1 genotype if you have 5. You got to be little f, little f. Little f, little f. Genotype gives you the phenotype of having 5 fingers. But people with 6, they can have 2 different genotypes. They could be big F, so they got 2 dominant alleles. That's homozygous again because they're the same. So they're homozygous dominant this time. So they got a big capital F from their mom and a big capital F from their dad. Gives them 6 fingers. Now, the other possibility is you could have capital F, dominant allele, and 1 lowercase allele. So they got a capital dominant allele from one of their parents and they got a lowercase recessive allele from the other parent. Whenever you have two different alleles, a recessive and a dominant, that's called being heterozygous for the trait, or they also call it being hybrid. So heterozygous and hybrid mean the same thing. Now moving on to the pictures on the bottom. This little dent on that girl's face, that's called a dimple. Dimples are dominant traits. So we will signify that with a big D for dimple. Now this guy over here has no dimples, and we will signify that with a lowercase d. So the only way you cannot have dimples, you've got to be what's called homozygous recessive. You got to have two little d's in order to not have dimples. That would be your genotype. So the only genotype you can have to not have dimples is homozygous recessive or little d, little d. Now remember, those of us that do have dimples, not me, but those of you guys, if you do have dimples, you can have two different types of genotypes. You could be big D, big D. So you got the dimpled allele from both parents, or you could be big D, little d. So you got one dimpled allele, the dominant allele from one of the parents, right there, and you got the recessive no dimple allele from your other parent. But it doesn't matter, since it's dominant. Whenever you have, it doesn't matter if you have two dominant alleles or just one. These two right here will have the same phenotype of having dimples. So it doesn't matter if you have two big D's, that doesn't mean like you have more dimples or your dimples are deeper. No, they're the same. You can have two dominant alleles or just one. Doesn't matter, you still have the same phenotype of having dimples. All right, on to the Punnett squares. So Punnett squares, you use them to help determine the probability of different genotypes and phenotypes in the offspring of two parent organisms. So probability, what is probability? These are obviously quarters, and I'm guessing you've probably flipped a quarter to see if it's heads or tails. Well, the probability of that is 1/2, or 50%. It's 50% chance of flipping a heads or flipping a tails. But what if you flip two coins at once? Now what are the chances of both of them being heads, or both of them being tails, or having one with the heads and one with the tails? What are those probabilities? So remember, in genetics, when we make our gametes, we only give one of our chromosomes to our gamete. We don't give both. We don't give both pairs. We just give one of the two. So this Punnett square is going to help to determine what's the probability of giving different traits in your kids, like dimples or blue eyes or 6 fingers or whatever. So this is how it works. Whenever you flip a coin, you know there's only two outcomes that can happen. You can get a heads or you can get a tails. So, same thing with our genes, our alleles. There's only two options. We can give the one from our mom that we got from our mom, or we can give the one we got from our dad. So, if we flip a coin, we can get a heads or we can get a tails. When we flip the second coin, it's the same options. You can get heads or you can get tails. It's not going to land on its side and stay balanced and not be neither head or tails. It's going to be one of those. So with these Punnett squares, all you do is you fill in the boxes. First you put the two possible outcomes on the sides, and then you just fill in the boxes. So this box would be H, 2 heads. This box over here, you bring the H this way and the T comes down. So it'll be H, T, heads and tails. Same thing with this box. We'll bring the heads from way up there and the T's right there, heads and tails. And this very bottom right box, the T comes all the way down, and this T comes across. It's going to be tails, tails. Now all you do is you count them up. What are the chances of both quarters being heads? Well, there's one that's head, and that's it. 1 out of 4 chance you will get both of them heads. What are the chances of getting heads, 1 heads and 1 tails? Well, there's 1 right there, and there's 1 right there. So that is 2 out of 4, or 1/2, or 50%, whatever you want to, however you want to say it, means the same thing, are going to be 1 heads, 1 tails. And last, what are the chances of just getting 2 of them with tails? Well, there's only 1 out of 4 boxes has tails, tails. So that goes back to 1 out of 4 chance of getting a tails, and the other quarter being a tails. So that's how it works. But remember, we're not going to be using coin flips. We're going to be using genes or alleles. All right, so now we'll try one for real. So here we got 2 rabbits. We're going to cross these 2 rabbits up here. So we're going to cross a black rabbit who is homozygous for black. So it has the genotype of big B. And we're going to cross that with a white rabbit. And since the white allele is recessive, we know its genotype. It has to be little b, little b. All right. So all you do is put their alleles, doesn't matter if you put them on the side or on the top, you just got to keep them together. We'll put the black rabbit's alleles on the side. So we're going to segregate them, we're going to separate them. So we're going to put 1 big B there, 1 big B there. We'll put the white rabbits on the top. Doesn't matter, they could be on the top or the side as long as they stay together. Let's segregate its alleles. Little b right there, little b right there. And then you just fill in the boxes. So we're going to put this box, the big B in there, little b. And you can see they're all going to be, put the big B there, bring the little b down, big B over here, little b, and of course this one, last box, is going to be big B, little b. Now, genotypic ratio just means how many out of 4 are going to have each genotype. And if you look, all 4 have the same exact genotype. So the answer to that would be 4 out of 4, or 100% of these baby rabbits are going to have the genotype of big B, little b. All right, now phenotypic ratio. All that's asking is, what are these rabbits going to look like? And since all of them have 1 dominant black allele, they're not going to be gray, they're not going to be black and white. Since this is dominant and recessive patterns, since they all have 1 dominant black allele, 100% of their baby rabbits are going to be black. They're going to have black fur, and they're all going to look like that guy. Now we're going to try crossing 2 of the babies that we had from the previous slide. So if you remember, 100% of the baby rabbits have the genotype of big B, little b. And we're going to cross that with another big B, little b, heterozygous. Heterozygous means different, 1 big, 1 little letter. And they're both going to be black because they both contain the dominant big B black allele. So just like always, we're going to segregate. We'll put this guy's alleles on the side, big B, little b. We'll put this guy's alleles up on top, big B, little b. And then we just fill in the boxes. So this big B comes down, big B. This big B comes in, big B. Fill in the next box, big B, little b. This one, the big B from the top is going to come down, and the little b from the side is going to come down, so big B, little b. And the last one, the little b from the top is going to come down, and the little b from the left is going to come down. So it'll be little b, little b. Now, here we go, genotypic ratio. How many out of 4 have each genotype? So let's just count them up. How many of them have the genotype of big B, big B? I see 1, I see 1. 1 out of 4, on average, will have the genotype of big B, big B. All right, let's do the next one. How many have the genotype of big B, little b? I see 1, I see 2. So 2 out of 4, or 1/2, will have the genotype of big B, little b. And the last one that's left, on average, 1 out of 4 will have the genotype of little b, little b. Now, what are the phenotypic ratios? It's basically saying, what are these little baby rabbits going to look like? Well, this guy's obviously going to be black because it has two dominant black alleles. This guy's going to be black because it has one dominant black allele. That's all you need. And this one's also going to be black because it has one dominant black allele. So that looks like 3. So 3 out of 4, or 75%, will have black fur. The last one right here, this rabbit right here, little b, on average, when you mate these two rabbits, 1 out of 4 of their baby rabbits, their offspring, will have white fur. Now I know what you guys are all saying. Aroso, these look fun. Can we try one for ourselves? Sure, go ahead and try one. Let's see if you can try this one. You're going to cross two plants. One that is heterozygous tall, and we're using the letters T, and one that is a short plant. So step 1 is find the genotype of the parents. Let's see if you can fill this whole little box out. All right, so heterozygous tall plant. Heterozygous means different. And since we're using the letter T's, this plant is tall, but it's heterozygous. So it's going to have one big T, one little t. And we're going to cross that with a short plant. Since short plant is recessive, the only way it can be short is it has to be two little t's. All right, so now let's put their alleles on the side and the top. So we'll put this guy on the side. So we have the big T, little t. And we'll put this guy on the top, little t, little t. Now it's just fill in the boxes. Big T from the left, little t from up top. This box right here, big T from the left, little t from up top. This one down here, little t from the left, little t from up top. And the same thing with this one, little t from the left, little t from up top. Now, what are the genotypic ratios? How many of them are big T, little t? I see 1, I see 2. 2 out of 4, or 1/2, or 50%, have the genotype of big T, little t. Now, how many are little t, little t? I see 1, I see 2. So 2 out of 4, or 1/2, or 50%, will have the genotype of little t, little t. Now, what's the phenotypic ratio? So these guys right here, since it has one tall allele, and this guy has one tall allele, that's all you need. Since it's dominant, all you need is one tall allele to make you a tall plant. So 2 out of 4 of these plants will be tall. And these two guys right down here, since they have 2 recessive short alleles, 2 out of 4 of these plants, on average, will be short. And now one more for you to try. Hopefully you're getting the hang of it. Now remember, step 1 is always figure out the genotype of the parents. Turn these words into letters. So we got to turn heterozygous purple into 2 letters. And we got to turn hybrid purple into 2 other letters. Let's see if you can figure this out. All right, so hopefully heterozygous, hopefully you knew that heterozygous means different, and we're using the letters P for purple. Heterozygous means different, so that means we're going to have a big P and a little p. And we're going to cross that with a hybrid purple. Now hopefully you know that hybrid and heterozygous mean the same thing. So it's also going to be different. So we're going to have one big P, one little p. Like usual, we're going to put their alleles, one on the side and some on the top. So we're going to put a big P, little p, there on the side. And on the top, we'll put this guy's one big P, one little p. And then it's just fill in the boxes. This top left box, big P, big P. This box here on the top right, big P from the right, little p from the top. This box on the bottom left, big P from the top, little p from the side. And this box here in the bottom right, going to be little p, little p. All right, now what's the genotypic ratio? How many of these boxes are big P, big P? I see 1. So on average, 1 out of 4 of these flowers will have the genotype of big P, big P. How many of them are big P, little p? I see 1. I see 2. So 2 out of 4 on average will have the genotype of big P, little p. And that leaves us 1 left. 1 out of 4 will have the genotype of little p, little p. Now what are these flowers going to look like? This flower right here has 2 dominant alleles, so it's obviously going to be purple. This flower right here has 1 dominant allele. That's all you need, so it's also going to be purple. This flower right here has a dominant allele, so it's going to be purple. So I count 1, 2, 3. 3 out of 4 of these flowers on average will have the phenotype of being purple. Purple you can see. Also, this one right here, 1 out of 4 are going to have 2 recessive alleles. So on average, 1 out of 4 will have the phenotype of being white. Remember, phenotype is what you can see. You can see purple, you can see white. Genotypes you cannot see. Those are the specific alleles that are in the DNA of these plants. All right, thank you very much for listening. I hope you enjoyed it, and I'll talk to you next time.